Hello everyone, and thank you for joining me. Today we are going to dive into the world of Verilog and explore the various operators it uses. Let's start with basics. What is Verilog? It is a hardware description language, often abbreviated as HDL, which is primarily used to model electronic systems. You might notice that Verilog looks a bit like programming language such as C. However, I want to emphasize that it is fundamentally different. Instead of giving a processor step-by-step instruction on what to do, Verilog is used to describe the actual physical structure and the behavior of a digital circuit. Before we can perform operations in Verilog, we need to know how to write numbers in Verilog. The format follows a very specific structure: size, base, and value. Let's break that down. Size. This dictates the number of bit and must be written as a decimal number. If you leave this out, the default value is usually 32-bit. Base. This tells the compiler what number system you are using. You denote binary with B, decimal with D or capital D, hexadecimal, and octal. Value. This is the actual number written in the specified base. A handy trick is that you can use an underscore within the value to make long numbers easy to read. Let us see examples. 4-B1010, a 4-bit binary number that deposits a decimal 10. 8-HF, it represents 8-bit hexadecimal number. 16-bit D100, 16-bit decimal number. And next you have 8-bit binary using an underscore. Since you have 8 long bits, we use an underscore in between so that we can easily read the data. -8-D5, we generally do not call it minus, we call it a signed number. It's a 8-bit negative decimal number stored as 2's complement. We have various operations in Verilog. Let us look at a few: arithmetic operator, bitwise operator, reduction operator, logical operators, relational, sorry, it is repeated again, and shift operator. Let us look at what is arithmetic operator. It is used for standard mathematical operation. If any bit of an operand is unknown, x, the result of the entire expression will be x. We have plus for addition, minus for subtractions, star for multiplication, slash for division. Then we have modulus and power. Let us see the examples. Let us consider we have a 8-bit register that is storing a value 10 and an 8-bit register B that is storing the value 3. And we have a 8-bit result also. The result A plus B will return you 13. 10 plus 3, 13. 10 minus 3 will give you 7. Then 10 multiplied into 3 will give you 30. Then 10 divided by 3, or else what you call it, it is a division. It generally gives you the fraction. Then you have A modulus B. In this case, you divide 10 divided by 3, and whatever is the remainder, that is 3 3s are 9 and you are left with 1, you will get a remainder. This is for modulus. Then we have bitwise operators. These perform operation 1 bit by bit, comparing the columns between two operands. If your operands are of different lengths, Verilog will automatically add 0 to the shorter one. There are various types: bitwise not, bitwise and, bitwise or, bitwise XOR, and bitwise XNOT. Let us see how it works. We have a 4-bit register which has 1100 and a 4-bit register B which has 1010. Let us see how the operations work. First we'll see add. A and B together, you add it. So 0 and 0 gives you 0, 0 and 1. Sorry, we multiply it. 0 and 1 will give you 0. 1 and 0 will again return you 0. 1 and 1 will be given as 1. Then we have RS OR. We do an addition operation bit by bit. 0 with 0, you get 0. 0 and 1 will return you 1. 1 and 0 will again give you 1. 1 and 1 will be kept as 1. Then we have XOR operation. If you know an XOR truth table, it will be easy for you to do it bit by bit. 0 and 0 will return you a 0. 0 and 1 will give you a 1. 1 and 0 will give you a 1. 1 and 1 again will return you a 0. Not of A, or the Bitwise not. What it does is it takes the value of A and just negates it. So we get 0, 0, 1, 1. Next we have reduction operators. What reduction operator does is it is very similar to bitwise operator, but the functionality is different. Instead of comparing two operands, they operate on individual bits of single operand to squeeze out a one bit result. This is incredibly used for checking conditions across an entire bus. These are the various types of reduction operators we have. We'll see the examples so it will be easy for you to understand. We have a 4-bit register A which stores 1011. Let us see what is AND of A doing. It is taking res 0, 1 and 0. When you do a AND operation, the result will be 0. Then you have result equals 1. When you do a OR operation of all the bits, you will get 1 as the result. Then you have the XOR operation of A. So it will count for the odd number of ones. Here we have 3, so it is returning a 1. Logical operators. What are logical operators? When we need to evaluate conditions, we use logical operators. This can be treated as a non-zero operand as 1, that is true, and a false as 0. And if you have any x, it is unknown. We have logical AND, logical OR, and logical NOT. Logical AND will return a true only if both operands are true. In this case, for logical OR, if one of the operand is true, it will return true. What logical NOT does is, whatever value you give to it, it will invert the truth value. That means it will return a 0. Let us check how it is working. We have reg A as 1 bit 1 and reg B as 1 bit 0. And reg C is for your output. When we do a logical AND of A and B, you have 1, and for C we have 1 dash B naught false. It returns a false. And for A we have 1 dash B naught, and for B we have 1 dash B0 and 1 dash B1. When we do an OR operation, one of the operand is true, so we'll get a true. And for not of A, we get C equals 1 dash B naught, that is false. And here we have used a conditional statement here. If count is equal to 10 and enable is equal to 1, it will return a true. Relational operators. It is used to check whether true or false, those kind of conditions. What relational operator does is they compare the magnitude of two operands, also resulting in a 1-bit value, either true or false. Let us check. Here we have x as 4-bit decimal 5 and y as 4-bit decimal 8. We know that 5 is less than 8, so the result will be 1. It means it is true. Here 5 is greater than 8. No, it is a false, so we return 0. Here it is checking whether it is equal to 5. Since it is equal to 5, less than or equal to 5, we get a 1. Here again it is checking. If it is correct, it will return a true, or else it will return a false. Equality operator. This is used for checking logical equality. It yields an x if there are x or z bits, and same goes with case equality. So if you compare 4-b10x1 to 4-b10x1 using the logical equality operator, the result is going to be x. We'll see it in an example. See, here we have x. The third bit is the second bit is an x. Let us check how it is working. So we are comparing the equality, and the output is 1-bx because we have x in the data. Then again for the second time we are checking the case equality. Since true, exact bit for bit match including x, since both are matching, case equality is matching. That means all the bits in both the operands are matching. Shift operator. Shift operator, when it shifts the bits of your left operand by the number of positions specified by your right operand. Shift left and shift right, these always fill the vacated bit spaces with 0. Let us check how it works. We have our data 4-b1010. Let us see how what happens when we shift it to the left. When we shift it to the left, we get 0100. It means we are shifting it to the left and adding 1 0 to it. Now we'll shift it to the right. When we shift it to the right, we get 0 1 0 1. That means when for the vacant space we are filling with 0. Arithmetic shift on a signed variable. Here we have um, arithmetic shift right. We're not doing arithmetic shift left because see it is the same as logical shift left, so we are not doing that. For arithmetic shift right, it is shifted right and filled with a sign bit. Whatever was your sign bit here, that is again filled it to the last position. That is how arithmetic shift right works. Okay, thank you everyone. That concludes our overview on Verilog and its fundamental operators. Thank you for your time and attention. If you have any doubts and questions, please feel free to drop them in the comment section. Thank you.